Okay, so the things that people want to ask about today, we've got a couple questions from quiz 4, and then we're looking at graphing for both the Gibbs lab and the equilibrium lab, so we can start talking about those things. We're going to knock out these quiz questions first. Number 1 is one of our oldie but goodies that keeps coming back to haunt us. It's how much how much ice melts. So this one, if we're looking at quiz 4, number 1, and I'm just going to pull these numbers real quick. Oh, if I could read. 46 gram piece of ice at 0 degrees Celsius, 46 grams ice at 0 degrees Celsius is put into 123 milliliters of 60 degrees Celsius water. Does all the ice melt? What is the final temperature when everything is equilibrium? How much ice? Right, and these two questions are almost always asked in tandem. So this is an old, this is back to week 1, week 2 material. This question keeps coming back because people keep getting it wrong. So it just keeps coming back. I hope that people will get it. And these two questions almost always come in tandem because it's a one or the other. Either all the ice melts, so there's none left, and there's some final temperature we're calculating, or there's ice left over, so the final temperature is 0, and we're calculating how much ice is left. When we think about this, we're thinking about it in a couple different steps. We've got our insulated container. We've got our water. And we've got our ice. Right? And so when we think about the energy, if this was an insulated container and there was no energy coming in or out, we've only got two things that are going to happen, right? We've got the water that's hot and the ice that's cold. So where's the energy going to go first? It can't leave the container. So if the water's at 60 degrees, and I'm going to make the chunk of ice bigger. If the chunk of ice is at 0 degrees, which direction is energy going to flow?
Into the ice.
Into the ice, right? So our first flow of energy is going to be from the H2O into the ice. The ice is already at 0 degrees, so we're going to have the water's going to lose some amount of energy. Sorry, the water's going to lose some energy. And the ice is going to melt. That's not all, though. Right? So if we just do that step, that's fine. But when the ice melts, what does melted ice become?
Water.
So when the ice melts, it becomes a layer of water at 0 degrees. What's going to happen to that water at 0 degrees? It's also going to heat up. We're going to have another flow of energy from our hot water into that layer, if there's enough energy for that to happen. So we're going to end up with a second MC delta T equals MC delta T. Where I'm going to be a little bit careful, this is like the water system, and this is the ice system. Right, and since this is the same water system, I can kind of put these together, right? This is going to have a small delta T, this is going to have a larger delta T, but since it's all the same system, I can really just put this together as my water is losing energy twice, so I'm going to have this MC delta T for the water equals the N delta H plus the MC delta T. I'm calling it ice. I'm going to switch this from ice just because I'm just going to call it 2. Because I don't want us to get it confused, because that second one, it's not ice, it's the melted ice. It's not ice anymore, it's water that's heating up. So I don't want to give it, even though it's our quote-unquote ice system, I don't want us to get it confused with, oh, it must be ice. It's just system 2.
Okay. Can you like re-explain like the 2 extra MCATs? I think that got me a little bit confused.
Yeah, okay. So essentially what we're looking at here is whenever we've got an MC delta T, that's for energy being lost.
Yeah.
Right? So energy is being lost from the water, from the hot water into the ice, and it's being lost from the hot water into the melted ice. So if we could somehow, you remember when I did this, I had ice in a plastic baggie, and I like put it into the hot water, I took it out some point, and it's like, oh, the ice melted, but it's still cold, right? I took it out of thermal contact, so the melted water that was in the baggie couldn't get any hotter because I took it out of the hot water. But if I put it back in, eventually they balance out to the same temperature. So not only does the ice melt, the ice also warms up. And the energy is being lost from the water both times.
So this is, okay.
So these two things we can put together as one. Right? So it's like T final 1, T final 2. We can put these two together. Since they're both the water losing energy, we can just say it's one big energy loss from the water.
Okay.
And it's going to go into melting, and it's going to go into that warming.
Okay.
Question?
And so how do we know to use this instead of enthalpy of fusion? Or is that applicable to this as well?
It is applicable to this, right? So when we look at this delta H, we say, okay, well, what is that delta H for a phase change? This delta H is going to be the delta H of fusion, right? Recognizing that H2O solid to H2O liquid, that phase change equation has a delta H associated with it. And that delta H would be the delta H of fusion. And so delta H of fusion is tucked inside of there. It is there. Great. So that is kind of the thinking setup, right? I've got this isolated system of a piece of ice and hot water. The ice is going to melt. Then it's going to turn into water. The water's going to warm up. So my water's going to, my hot water is going to cool off. My ice is going to melt, and my melted ice is going to warm up.
Okay, gotcha now.
Right?
Makes more sense.
And it's funny to break it down in this way because we've all put ice into our drinks to cool off our drinks and seen the ice melt, or put too much ice so that not all the ice melts. And we've never really thought, like, could I calculate the exact right amount of ice to get my drink to the temperature I want? And the answer is yes. This is how we would calculate the exact, if we wanted to get to an exact temperature, we can figure that out. We used this scientifically to say, well, what if we didn't know? What if we were doing something besides water and we didn't know this delta H? We could experimentally figure out what that delta H was. Or what if it was something where we didn't know the heat capacity, and we could use this to experimentally figure out the heat capacity. So there's those different things we could do. But this problem is just saying, does all the ice melt? Can we keep track of this energy flow idea? So at this point, I'm going to switch to blue to be dramatic. We're just going to start plugging in different things. Since it's water, I know the density of water is going to be 123 grams. I know a gram per milliliter. My heat capacity is going to be 4.184 joules grams degrees Celsius. My delta T is going to be final minus initial, where I don't know T final, but I know T initial is 60 degrees Celsius. I didn't give myself enough space, so I'm just going to continue it down here. My N, this right-hand side, is for the thing that's gaining energy. That's going to be my ice. So that's going to be 46 grams times 1 mole is 18 grams. Molecular weight times the heat of fusion. I can't remember right now if it's 40 or 6.01. So I need an equation sheet, which I think I have one right here. delta H of fusion is 6.01. Because I want the units to match, right, this is 6.01 kilojoules per mole. And right away I can see I have a unit mismatch because I've got joules and kilojoules. So I'm just going to do a quick conversion in my head. I'm going to turn this into 6010. Well, let me give myself a little more space. 6010 joules per mole. And then I've got to do my M2C2 delta T. That's different than the water. It's the ice system, but it's the melted ice system. So that 46 grams is still going to be 46 grams. The part that really throws people off, we use the heat capacity for the melted phase. So it's still 4.184 joules grams degrees Celsius. T final is still not known, but the initial is 0 degrees Celsius. And that 4.184, that's a big problem that people have. It's just like, why is it 4.184?
It's because it already melted, right?
Already melted, right? Notice our ice started at 0. The place, we could make this problem more complicated. We could have the ice be cold. And so you have to warm up the ice to 0 before it melts. And then you would have another MC delta T for the solid ice. But we skipped that. We said the ice is already about to melt.
And if you did that for the delta or for the heat capacity of the ice when you're heating it from the really cold to the 0, you use the heat capacity of ice and the
Yes,
water. Okay.
exactly. So you'd have to use the heat capacity for solid H2O. Right, now at this point I made one mistake. Do you all see the mistake? It's the one that I always make. I almost did it on purpose, but I didn't do it on purpose, then I left it on purpose. Yeah. Remember, one thing is losing energy, one thing is gaining energy. These arrows of energy flow are directional. So these aren't just equal to each other, they're equal and opposite. One thing loses energy, the other system gains as much energy as the other one loses, because it's isolated. There's no other place energy is coming from or going to. So don't forget that negative sign. At this point, we're just doing algebra. We've got all our units taken care of. And we're just doing algebra. At that point, hopefully it's easy. Now, we can also put in some logical boundaries. Temperature has to be someplace between 0 and 60. It shouldn't be negative, and it shouldn't be greater than 60. So if we get something that is below 0, we've got a problem. If we've got something that's greater than 60, we've got a problem. Right now, if it's below 0, that means how much ice is left is not 0, right? With the way that I set this up right now, I assumed all of the ice is melting, right? I've got here, I'm using all 46 grams is melting. But what if that's not true? What if there's ice left over? Then this becomes a variable. Instead of this being 46 grams, that would be a variable, like x, but my final temperature would be 0. I don't think that's the case, because there's a lot of hot water. So I can kind of logically look at this and say, there's like 4 times more water at a high temperature. You put a little bit of ice into hot water, all the ice melts, the water cools off. So kind of use some logic of experience with the real world to say, look, right, if this was 23 grams of hot water, I'd be like, oh, I'm putting twice as much ice into water. Then I might have some ice left over, temperature hits 0. But with that amount of water, I feel like this is a pretty safe way to go. It's always worth it to slow down and be like, what's a logical result? What makes sense for, like, can I get negative temperatures in this case? Can I get temperatures bigger than 60 in this case? Before we start punching things into the calculator. For fun, I will tell you the final answer to this, if you do the calculation correctly, is 21.9 degrees Celsius. Okay, should we go ahead and look at number 2 and then we'll go on to Gibbs Lab? Any other questions on this one before I erase? Okay. Okay, so Number 2 on quiz 4. If you're watching this in the future, i.e. next quarter, and you're looking at this before quiz 4, stop the video. Do the quiz first. Okay. Number 2 on quiz 4. And I don't know if you all have looked at my old lab YouTube videos, but quiz answers are on there. No one thinks of that beforehand, thank goodness. Okay, so this is, this one. Okay, so this is one of those comes back over and over. I think this has been on every quiz since week 2. So this is one of those. Select the words positive, 0, negative, or unknown for the boxes when adding a solid to water, when an insoluble salt with the absolute value of the lattice enthalpy is less than the absolute value. What is the signs for the Gibbs energy, enthalpy, entropy? So we're putting a solid, this is discussing the solubility reaction of a salt going into water. I don't think I rephrased this well. I tried to rephrase it so that the process was first, because it used to put the process last, and that seemed to confuse people. So I tried to put the process first. The point is, we are putting a solid salt into water when it's insoluble. So I'm just going to make up a salt. I'm going to do it, let's see, we're going to call it metal with anion. It's a solid. And it's going to break apart into metal plus aqueous and X minus aqueous. So it's an ionic solid. This is the reaction. At this point in the quarter, we know that we should do a double arrow and there's some equilibrium between the products and reactants. But, this problem wasn't about that. And now it says, okay, what's delta G? What's delta H? What's delta S? Positive, negative, or unknown. Now, first off, it tells us the thing that is important about this is there's no math. These questions are purely conceptual, connecting key terms to what's going on. So we have to have that nice comfort with key terms and vocabulary, not as independent ideas, but as a collection of ideas that relate to each other. So when I see that we are looking at a solid dissolving and it's insoluble, that means it's going to stay as reactants. That means that this is going to be non-spontaneous. Delta G is going to be positive. Right? We get that because, right, without doing anything besides thinking about it, right, it's insoluble, it stays as reactants. So I can tell that right away. Delta H, a little bit more complicated. That's where we get these weird things. The absolute value of the lattice enthalpy is less than the absolute value of the heat of hydration. Question?
Yes. Are there any cases where there is an insoluble salt and the delta H is a negative?
The delta G?
Yeah.
Yeah. If
G.
we were talking about ions forming into solid, if we flipped the reaction, yes. But if we are talking about the solid to ions, insoluble is always going to be positive.
Okay.
Question?
The reason this is so confusing for me is because it's under I understand that lattice energy is discussing how hard it is to break up a compound.
Mm-hmm.
And in this example, so it's an insoluble salt, which
Mm-hmm.
means it's hard to break apart, but the hydration is greater than the lattice, which means it absorbs water well.
Well, let's talk about what this means. So when we think about our hydration, we can think about it in terms of delta H of lattice plus delta H of hydration. Now, your thinking is pretty good, but the delta H of I think you're putting it together too much, right? The delta H of solution is about these two processes together. The delta H of lattice is how hard it is to break apart the solid. The delta H of hydration is how well do the ions attract water to them. So the lattice is always a positive. It always put energy in to make that happen. And the hydration is always a negative. We always get energy back as it attracts things towards it. Now, the question is, which is bigger? And I do this little cartoon system for this. The absolute value of the lattice is less than the absolute value of the hydration. So the heat of hydration, and I just do this, I make this a bigger negative. So I can tell which one's bigger. I can even, if I want to be really dramatic, I'll make this smaller, right? So it's easy, so this is weird, right? It's easy to break apart the crystal structure, but then when water attracts to it, the water is really attracted to the ions. So there's this imbalance. I'm making it a little dramatic. So I would overall expect this to be little positive, big negative. This is all overall going to be negative. In truth, right, I'm making this dramatic. In truth, it's probably a very small negative. It's probably very close to being 0, but it's not exactly 0. It's a little negative. It's a little exothermic. We actually saw this in our solubility lab with the calcium chloride, right? We put calcium chloride into water, we saw the temperature go up. Kind of weird. Most salts are not like that. There's only a few examples of exothermic solubilities. Calcium chloride happens to be one of them, and we use that in the lab. Normally, it's overall positive. That's more common. So it's okay if you're like, wow, I really thought that if the delta H of lattice was big, the delta H of that's like the delta H of lattice is typically larger, but not always. Question.
So then, if the question stated that the absolute value of lattice was greater than the absolute value of the hydration enthalpy, then would it be a positive
small
delta H?
negative,
Okay.
overall positive. Yep. Exactly. Overall endothermic. Now, this is positive, this is negative. To get my delta S, I can think about it kind of 2 different ways. Let me think about this. No, I don't. I was thinking about writing it a completely weird way. I think that's a bad idea. Right, I'm going to go back to the way we normally think about it, right? So we normally think about it like this. And I thought about just rearranging it. Tell me if this is a bad idea. I've never done it like this before, and this is the first time I ever thought about it. If I just add this over and subtract this over, so I had T delta S was equal to delta H minus delta G. Right? Now, I know my delta G is positive. I know my delta H is negative. No, I don't like this. Unless it is actually unknown. No, I don't like this. Okay, let's go back to the normal way. I shouldn't try and do things while I'm recording. Okay, so we know that delta G has to be positive. We know that delta H has to be negative. Now, the only way that this is possible, right? If T delta S didn't exist, we've got an impossible situation. So I need to add something that's bigger than delta H to this. So I need to add to this. So I've got a minus T delta S. How am I going to make that addition? Delta S has to be negative, right? So delta S has to be negative, so that way instead of it just having a subtraction, I need it to be positive, I need to add. So I'm going to have a minus and a minus. So delta S has to be negative, and it never asks for this part, but I really like this part. T delta S has to be bigger than delta H.
This is where I get a little confused sometimes because I think of this as a whole and I see like another negative right there and I don't know.
Yeah, well, so there is a way you can do this where, again, depending on how your brain breaks it up, like you can do plus negative T delta S. And then you got your negative and negative, so then it becomes addition. But that's just not how we usually see it written out. Some people writing it like this really helps them in terms of thinking about how the signs affect each other. For some people, this is just extra confusion.
Okay. Does that sign affect these signs or no?
No, this is just part of the definition.
Okay, gotcha.
So if this is negative, then we're just doing a minus times a minus.
Okay.
And it becomes positive. If this is positive, then it's a minus times a positive. It's overall
Okay.
negative.
Gotcha.
But I usually have it written down like this, just because that's the typical way we see the equation. And I like doing this kind of like, do I need to think about adding or subtracting from delta H to get to a positive? I need to add because it's already negative. So I need a minus of that minus. I need to subtract a negative. Weird phrasing. Math. Ugh. So we know that delta S has to be negative, and T delta S has to be bigger than delta H. It doesn't ask us for that last thing, but I think it's an important detail. This reaction, depending on how big that temperature is, could be flipped from spontaneous to non-spontaneous. This was all done at room temperature, so at room temperature it's non-spontaneous. What if we cranked the temperature up or down? How would that affect it? This question's not asking about that. This is just at room temperature. T delta S is greater than delta H. Delta S has to be negative, otherwise this reaction would never be non-spontaneous. Okay. Questions about that before we start talking about Gibbs?
I think I do. 'Cause I think before we talked about how delta G can be unknown sometimes with like two negatives. Like
Keep going.
what cases like how would we know it would be an unknown for like
So
certain things?
the place where we typically see an unknown is the delta S.
Okay.
Right, the delta G and delta H are both very experimentally observable. Like, does it happen or not? Does it get hotter or colder? The delta S is typically the thing we see go unknown. And so the place where that would happen, let me just do a quick example of that. Right, if we had the delta G being positive and we had the delta H being positive, right, when they're the same sign, what do I need to do to have delta both sides be positive?
You could do like either.
I could do either. It's already true, right?
Yeah.
It's already true, so I don't need to do anything. So if I'm adding more stuff, it becomes more positive.
Okay.
That's fine. If I'm subtracting a little bit, that would also be fine.
Okay.
That means delta S could be either thing. It doesn't really matter what delta S is. It could go either way.
Gotcha.
And so those are the situations where we end up with unknown for one of them.
And that can happen when they're both negative as well, right?
That can also happen when they're both negative. Whenever delta G and delta H are the same sign, we run into that case where there's like, oh, delta S could be the same sign, or it could be the opposite sign, and it's just how big is it.
Gotcha. Thank you.
Okay. Do you have more questions too?
Yeah, but we can look
Hang
at
on
them
just a second.
later, because I just